Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Well, Houston, we don't have any problems. Today we want to talk about acceleration. But as we talk about acceleration, the first thing we're going to look at it is we're going to look at it how it might look graphically, because graphs are awesome. Now you might recall that when we were first learning, we learned about distance time graphs, right? So we've got distance versus time. Sometimes we call this delta x, same thing, which is weird because this is the y-axis. We talked about how, you know, if I'm traveling like this, right, then I am traveling at a constant velocity because the slope of the line is the velocity, right? Because v is d over t, actually delta d over delta t. And so what I've got going on here is that's the velocity. But now we're talking, this axis over here is not distance, but take a look down here. The axis is actually velocity. So if we're talking about velocity, these lines, though they might look similar to what we saw before, are actually, well, they're quite different. So let's take a look at this object right here. What's the object, or the velocity of the object at t equal to 5 seconds? So if we come down here, we find t equal to 5 seconds. We come up right here, and what do we get? That's right, the answer is 25 meters per second to the north, because this, by the way, is velocity in the northern direction. What about at t equal to 7 seconds? So we'll come to 7 seconds, that's about right here. That's also 25 meters per second. Do you see that? That this is also 25 meters per second. What about t equal to 15? So 15, we come right here. The velocity is, looks like 35 meters per second to the north. And at t equal to 25 seconds, we're back to 25 meters per second. Now, that's a little bit tricky. Now, what about that one? 25 meters per second, that's still to the north, okay? So it's just reading the graph, velocity versus time. So now let's talk about acceleration. Now, we haven't really talked too much about what acceleration is, a little bit. Acceleration is the change in velocity divided by the change in time. So if you think about this, velocity is here and time is here. So acceleration is the slope of the line. Does that make sense? So which time interval has the greatest acceleration? Calculate the acceleration from that time interval. So what we're looking for is we're looking for the steepest part of this curve. This right here, of course, is slope is 0. So there is no acceleration right here. We'll talk a little bit about what this means. So the steepest part of this is this beginning part, right? So it's from here to here. All right, so that's the time interval is from 0 to 5 seconds. So 0 to 5 seconds. So if I want to find the slope of that line, which is the rise over the run, so the change in the velocities, he went from 0 to 25. So the 25 minus 0, that's v final minus v initial divided by, and that'd be, this is, delta t. Delta t is t final minus initial, and that would be 5 minus 0. So 25 minus 0, 5 minus 0, of course, is 25 over 5, which is 5. Now units on that would be meters per second squared, and this is a vector, so we would say to the north. So here's something really intriguing. When you are looking at a velocity time graph, and we'll learn more later about the mathematics of this. In a velocity time graph, the area under the graph is the displacement, the distance from the origin. Isn't that like cool and interesting? So let's see if we can figure out what that would be after 15 seconds. So if we jump to 15 seconds, essentially what I want to do is I want to find the area underneath this shape, right? So this sort of weird looking shape. And the only way I would do this is we're going to use some simple geometry. All right, so let's find this shape first right here. So this shape is a triangle. Remember, the area of a triangle is base times height, it's an h height, divided by 2. All right, this is a triangle, it's a right triangle, so the height of this triangle is, each of these lines, what is this, 5? So this is 10 by 5, right? Let's just label our squares and stuff like that. And this right here would be 5 to 15. This would be a 10 right here, right? By and the height would be 25, right? And this triangle would be 25 right here, this triangle here, by 5. Okay, so let's do this one first right here. So that would be, so I'll say the baby triangle, if you will. That's 10 times 5 divided by 2, right, because it's a triangle. So 10 times 5 is 50. 50 divided by 2 is 25 meters, because it's going to be just distance. This triangle right here, we'll call this the tall triangle, right, like this one, which was, what was it, 25 times 5. So that's 25 times 5 divided by 2. All right, get the calculator out here. 25 times 5 divided by 2 gives me 62.5. And then we have now just a rectangular shaped object, which is 10, right? That one is 10 by 25. So 10 times 25, that's 250, right? I'll do that. So then we're going to add each of these numbers up. So 62.5 is on my calculator, plus 250 plus 25, total distance. So we'd say delta x, right? Or you could say delta d. I'm a fan, the computer in our system uses LX. I'm a fan of delta d, by the way, is 337.5. So let's now talk about what these graphs might look like when we're talking about comparing graphs, right? These are the dt graphs, and these are the vt graphs. So for the same different thing. So let's talk about what it looks like if you're stopped. If you're stopped, if you recall, in the distance versus time graph, that's just a flat line at x equal to 0. All right, and velocity time graph, it would have to be at 0. If you're at this spot right here, then this is stopped. So the graphs look the same if they're stopped. It's actually the only one where they look the same. Let's talk about at constant velocity. So if you're at constant velocity, so this is an interesting one. Constant velocity, if you recall from a distance time graph, is going to be a straight line either up or a straight line down. What's going on here, this is moving in the positive direction, right? Positive velocity. And this is negative velocity. This is a review, right? But what does it look like on a VT graph? Here's the interesting thing, is that at constant velocity will be a straight line, okay? A straight line, it could be any number, and it'll be a straight line because if you think about the slope of this line is going to be a constant number. So this is going to be a positive velocity in the right direction. So this is like 3 meters per second, right? Or what if this 3 is this thing? Now, as a note, you've also got the reverse down here to kind of compare to this. You can also have a negative velocity, but it'd be a straight line, but it would be below the axis, right? So the VT graph looks a lot different than the DT graph, doesn't it, on this case? All right, what about when you're speeding up? If you recall, speeding up in a DT graph looks like a curve. Now, or, of course, we've also got this one, right? And this is speeding up south. So this is, let's make a note here. This is speeding up, say, north. And this is speeding up south. You're still getting faster. So what would that look like from the perspective of a velocity time graph? Likely, you're going to have what we call constant acceleration. So now you're going to have a straight line. So each of these, right, so speeding up, this is speeding up north, all right, and this is speeding up south. But now you're going to have a flat line. That makes sense? So as A gets, as V gets further from 0 meters per second, the speed increases because they're going faster and faster and faster and faster, right? At first they're going 1 meter per second, and then 2 meters per second, and 3, and then 4, and then 5. So you're getting faster and faster and faster. That's what acceleration is. You're getting faster and faster and faster. Or you're getting slower and slower and slower because it's actually the change in velocity over time. So what about slowing down? Now, if you recall, we said slowing down towards the north looked like this, right? And slowing down from the south looked like this. So the kind of mirror images. So this is like, both of these are accelerating or maybe in the negative direction to a stop, right? So there, we might use the word deceleration. Deceleration is negative acceleration. All right, what might that look like in a VT graph? The interesting thing is this, is it's going to be also a straight line, but notice it's going to be like this. All right, so these are how these graphs might or should look, actually, when you are comparing all three. So let's summarize these speed time graphs by really looking what it might look like on sort of a big graph like this. So we've got this speed time graph. What's happening in each case? So right here, we start at time t equal to 0, and we're going to go to time t equal to whatever this is, time-wise, I don't know how many seconds. Oh, it's 2 seconds. So from 0 to 2 seconds, he's stopped. Because he's going 0 meters per second. So for the first 2 seconds, the person is stopped, right? So that's stopped at this juncture. But when we go from here to here, from t equal to 2 to t equal to 4, what happens is it's accelerating. Now let's think about this. So he is accelerating in the positive direction. And we can figure out what his actual acceleration is. We'll just take the slope from here to here. This is constant acceleration. It's 10 over 2, right? So, delta V over delta t is 10 over 2. So he's accelerating at 5 meters per second squared. So at the first, right, he's going 10 meters per second here, and he's going 20 meters per second here after seconds. So he keeps going faster and faster and faster. And then what happens at this point? Now notice this is an important point. This is not going at a velocity of 0. He is going at 20 meters per second. So we'd call this constant velocity. Constant velocity. Mr. Bergmann can't spell. All right. Now, what happens at this second at 6 seconds? From 6 seconds to 9. So this is from 6 to 9 seconds. What he's doing is now he is slowing down because he's going. So we'd say decelerating because his slope, right, is negative. It's the same one here. I think it is. Well, let's do it. 6 to 6 to 8, he goes from 20 to 0, so it's 20 divided by 2, right? He goes from 20 divided by 2, he's decelerating at 10 meters per second squared, but it'd be negative 10 meters, so he's slowing down 10 meters per second squared every second, okay? So that's pretty interesting. Is that right? And then what's happening right here during this juncture? He's stopped again. So he's come back to 0, and as he's 0, if it's flat at 0, he's stopped. So he stopped his car, or whatever it is. And at this point, now what happens from here to here? He is now moving at a constant velocity. But what's the constant velocity? It is going to be negative constant velocity. So he's going a constant velocity, if you will, in a negative direction, so let's say to the south. And the slope of the line would help us determine how far south that is, or what that speed is. We could figure out what that is. It would just be the slope of this line, and that would tell us how fast it goes. So let's see if we can describe what this might look like. So in that last box, what I encourage you to do, let's see if we can kind of come up with a story. So you're at a car, some guy's at a car, and let's say this is to the north. He's traveling to the north, but for the first 2 seconds, he's just sitting at a light, let's say. Then he hits his accelerator because the light goes green and he goes woo! And he goes faster and faster and faster until he gets to 20 meters per second. And then he goes at a constant speed. He accelerates to 20 meters per second. He doesn't keep going faster because he's going to get the speed limit's 20 meters per second. He's going to get a ticket. And then what happens? Well, all of a sudden, let's say right here, he hears some sirens. And what do you do when you hear sirens? You slow down because you've got to get off to the side of the shoulder as the ambulance comes by or whatever. And so he decelerates, he slows down, and then he pulls over and he stops for this interval. I think it's just 1 second as the emergency vehicle passes. And then for some reason, who knows why, he turns around and he goes back the other direction. He decides that maybe there's an accident and he needs to turn around, and he starts to accelerate in the opposite direction. I guess we don't have time here for him to turn his car around, so he backs up in a faster and faster rate. Not really reasonable, but that kind of gives you a story of what this particular graph could describe. All right. So understanding graphs, even though this isn't technically part of our full lesson, it really is going to build us to understand acceleration, because the graphical understanding helps us to like figure it all out. And don't forget what else we could also do: how far as he traveled. It's the area under the curve. Now, if you think about how far as he traveled here, this would be an interesting one. I see, just side note. You would take this area right here, right, and then you would subtract this area because he's come back somewhat to some point where he has left. Houston, no problems. We'll see you in class.
Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.